All right, sorry guys. Let's try this again. All right, that is now not an open app. Let's try quit preview. I have no idea why this is happening, by the way. Homework answers, homework 5. Okay. Share screen. How does that work?
We can see it now.
All right, good. Sorry, guys. I'm not sure what that was about. Anyway, so the variance in P1, we're going to again go through this intermediary A1, which is the number of A1 alleles. The variance in A1 looks like PQ times the number of samples, which is 2n. So we get 2n PQ. So that's supposed to say variance, by the way. The variance in P1 is equal to the variance in A1 over 2n. I can pull out that 2n as a 2n squared and get the variance is 2n p q over 2n squared. The 2n's cancel and I just get p q over 2n. Only our p is complicated by this little factor r. Does this all make sense to everybody? It's all very, very simple. It is nothing but binomial sampling. Nothing has happened here. Up next is Julie with problem 5.
Sure. Oh, sorry, I have upgraded the system, so I have to reallow system preferences.
I know exactly what you're doing.
Oh, I have to quit. Sorry.
All right, see you again. We'll give you the next problem after. No, we'll wait for you. Bye-bye. Come on back. Technology, guys, it's lovely. There is a fear right now that that the first few minutes of this class is not going to be properly recorded. I think it is. I think I'm just going to be able to post this in 2 batches, but we will. If at any point we're missing the first 15 minutes of class, it was because I was stupid enough to get out and get back in. But I think
it did say recording stopped when you left, so it was recording at least.
Yeah, no. As soon as I stepped out, so the process turns out to be like it records, and then once the meeting ends, my computer does a whole lot of like transcoding to turn whatever it recorded into an MP4, and then I upload the MP4. So when I stepped out, it started immediately transcoding. I told it to pause, and then I realized that was a mistake, and I let it go. So I think the transcoding was okay, but when I came back in, it mentioned, you know, you're still transcoding and I'm trying to start recording again. Is this really what you want? I said yes, but we'll find out whether it all worked out. So, you guys understand. All right, so was that nice noise, Julie, coming back in?
Yes. Am I still going with problem 6?
Yep. We waited for you.
Thank
Didn't want you to miss anything. Didn't want you to miss anything.
Oh, or was it problem 5?
It's problem 5.
Yeah, okay. So for A1, it's 100% of getting an A1 allele. So it's 1 times P0 squared times R11. And then for A1, A2, it's 50%. And for A2, it's 0%. So added together, it's P0 squared R11 plus P naught Q naught R12. So that's the R value. And then plug into the expected value P naught R, we get this one.
Beautiful. That's it. So here we started out thinking we were sampling genotypes according to something that looked like the genotype frequency times some number. And then we found if we sample genotypes in that fashion, we can think about it as just sampling the allele with a different value of R, or with a knowable value of R that is a function of the probability of sampling the genotype. Does that make sense? So those R values are like proportional to the probability of sampling, or they are in this case, the probability of sampling the genotype times its frequency. And then we get to the probability of sampling an allele. Clear? So simple. You guys really just couldn't believe I asked that. All right, you're up next, Jim, with the next problem.
Okay. So this question was, substituting in this W capital term or lowercase. And so I just kind of put that in as directed into the equation and try to get W back out, right?
Yep.
So when you do that, and like as it says in the problem, that this whole thing equals 1, you get this situation, and then it ends up just being W maybe?
Oh, look at that. All right. Boy, what
Sure,
that was.
right.
That was all right. I made you do that. I'm sure. Why not? I made you do that. Maybe I'll have a reason later. But at the moment, I made you do that. Okay. It is as easy as you said. If I take the probabilities R and I multiply them by W, like something that sums to 1 multiplied by W is W. Okay, whatever. We'll see where I'm going with this eventually. But right now, I've just taken some numbers and multiplied them by other numbers for no apparent reason. Up next is Christopher with whatever we're on, problem 7-ish, 8. Christopher, make it? I thought he did.
Oh, yep. Sorry, I was muted. I'm just trying to share my screen here.
Yeah.
Okay, is that showing up?
Oh, yeah.
Okay, so just kind of plug things in here, I guess.
That's all you were asked to do.
So that's essentially how I did it.
Spectacular. And you got some term that looked like PW11 plus QW12 over big W. That's R. All right.
Yeah.
That's a nice, simple-ish formula. We still don't know what any of these things mean quite yet. But now we have something that looks like an allele frequency times something involving genotype A1A1 plus Q times something involving genotype the heterozygote, all divided by that constant W, is telling us where the population is going. When R is bigger than 1, if this quantity here is bigger than 1, the population is, the A1 allele is increasing in frequency. If R is less than 1, we know the A1 allele is decreasing in frequency. So we've probably just figured out that this term here, PW11 plus QW12 over W, is actually telling us whether the A1 allele is increasing in frequency or the A1 allele is decreasing in frequency. Whatever these W's mean exactly. Okay. But for whatever reason, we've now learned that those W's divided by the big W's weighted by the allele frequency is telling us which direction the population is going in, whether the A1 allele is increasing or the A2 allele is increasing. And we'll see that, I guess, more formally in problem 8. Kiana.
Sorry, I just lost the Zoom window.
Yep.
All right. Share. Great. So for problem 8, I just plugged in the R that we solved for above into P naught R. And that was it.
Shockingly simple so far. Now we got something that looks like the frequency of A1A1 homozygotes times W11 plus half the frequency of heterozygotes times W12 over W, whatever that is equal to the expected frequency of the A1 allele next generation. Again, it seems like we've done nothing here, and we have almost done nothing here, but we now have a formula that is giving us the expected frequency of A1 next generation as a function of a genotype frequency times something plus half of a genotype frequency times another thing over something else. I don't know what any of this is quite yet, but this has the look and feel of things that are going to look like Gillespie's book. Kevin, you're up with 9. How did that go for you?
Actually, one that I'm not.
Yeah, Kevin, this one got to be a bit of an algebra-y. Let's see how it started, and we'll see how it finishes.
Well, I kind of already knew what the equation was going to be.
Because you've read the book.
Yeah, you have to put P naught in terms of with the W, so that's kind of how I added it on, but this we already kind of know from previous things, so so this is what I got.
You just see your email, at least I did.
Yeah, dude, I'm looking at your student loan shit right now.
Oh, my bad. Oops.
Yeah.
Uh,
Almost something you surely don't want to be sharing with me.
Oh
Okay. Yeah. Now this is exactly correct. It is not as simple as it could be, but this is 100% a correct formula. You have started with the expectation of P1, and then you said the change is the expectation minus the value. So that formula is correct. There is 100%, there is no question that formula is correct. Gillespie presents that formula in a slightly uglier, different form. Did anyone bother to try to derive the form Gillespie presented it in? And does anybody want to try to show it?
Are you talking like with the?
Just doing algebra to make it look like there's a formula in Gillespie's book that says delta P is.
No.
Anybody bother to do that?
I think that I
No,
can.
then show it to us, Julie.
Okay.
This is
So
I'm very glad you did this.
yeah, I was just trying to derive that equation because it gave us directly.
Yep. Because that equation looks like it comes out of nowhere. It looks almost nonsensical when it is presented. Yet, walk us through this. What have you done? You started with exactly the formula Kevin started with.
Yeah, I have to remind myself. Okay, so I plugged in this W first for what we are given, and then I pull up a P naught from all these terms, and then I replace those 1 minus P naught with Q naught. Here's also another Q naught, and here's also another Q naught. So pull a Q naught out again, and then from the inside, it becomes this thing. And then, okay. And then you can group them by pulling out a P naught from these two terms, and then pulling out a Q naught from here and here for these two terms. So you can group them together.
That is 100% correct. That is the most efficient derivation of that. And this is like equation 1 in Gillespie in the book, equation 3.1 or 3.2 or whatever the hell it was. And it looks like it came from nowhere. In fact, it came from the above stupid things that we just did trivially. Like, why are you making trivially write down the frequency next generation and subtract the frequency of this generation, multiply top and bottom by a W to get, and then just do a whole lot of algebra. And suddenly you were at Gillespie's equation 3.1 or 3.2 or whatever he calls it. And this thing looks weird, but is almost interpretable. It looks like PQ, which looks like a variance in allele frequency, times P, the probability of A1, plus Q, the probability of A2. And here we have the difference in, well, we'll get to what these things mean, but the difference in WW11, whatever that thing was for the homozygote, minus whatever that thing is for the heterozygote, the difference between one homozygote and the heterozygote times P, plus the difference in in the heterozygote minus the other homozygote times Q, that thing normalized by the variance in allele frequency, normalized by something else, is going to give us the change in the allele frequency next generation. Thus, the change in the allele frequency next generation can be thought of as the difference in these things that we're going to call 1, 1, 1, 2, 1, 2, 2, 2. We're going to give them a name in a second. The change in allele frequency can be thought of as the difference in those things normalized by variance, normalized by this other thing we're going to give a name in a second. Does this all make sense?
Gillespie says that this is like one of the most important equations in all of population genetics, but he doesn't really say why. I'm wondering why he says that. Like, that's kind of a flashy thing to say.
It's because it's going to tell us everything we need to know about the fate of an allele under selection.
Mm-hmm.
You could almost say population genetics has only two questions. What is the fate of an allele when it's not under selection, and how does that change when selection happens?
Mm-hmm.
So in chapter last, 2, whatever it was, we spent most of the chapter thinking about what happens in the absence of selection.
Mm-hmm.
In this chapter, we work out what happens when selection exists. And this kind of sort of answers most of the fundamental questions in population genetics. It's going to be an application of one formula, one set of formula or the other, depending on what we're trying to model. And right, because we've just derived all of this in terms of binomial sampling, and we derived these formulas, just as a change in the binomial sampling probability, you might imagine that the way, if, like you're doing some hard problem in population genetics, what you're going to do is write down this horrible looking formula and maybe make an approximation to it to make it look like a little more linear, a little more like that R term that we started with, and therefore learn a whole lot immediately about what's going on. Mm-hmm. Even when selection gets quite complicated, like changing over space and time very fast. Mm-hmm. We may be able to get approximations to it by first starting with this and then randomizing over the next bit of randomizing things we're going to randomize over. And that's why it calls it one of the most, maybe the most important formula in population genetics. But he brought it out of nowhere. You guys see it's goddamn trivial. It was nothing fancy about it until you decided to do some algebra for no apparent reason. Despite the fact that you knew immediately what the answer was, it was the expectation of P1 minus just that thing at the top. Who cares? Well, you do a little algebra, you can write it in this form, which is maybe will be more informative in some circumstances. Okay, up next is Sebastian with 10. We're going to start talking about what these words, we're going to start giving these things words.
I don't think he's here.
Oh, oh yeah, no, I know he's not here. Qualifying exam. Young Song, are you here?
Sorry, I'm here.
Yep.
Whoops.
And guys, remember, if you ever run into my qualifying exam is due on Friday, the answer is blow off Cutler's class on Thursday. Like you write me the little email that says, by the way, I'm going to blow off your class on Thursday. And I'm going to write you the email back. Good luck with your exam on Friday. And this class is great. It's very important to me. It'll be important to you ultimately. But do not spend time working on your homework when you need to get your, sort of qualifying exam paperwork done, or you need to study for the exam or something. This is we can make this class happen at whatever time you need it to happen. When your qualifying exam committee asks you for something now, it has to be now. So always keep priorities straight and know for sure I will be supportive of you getting your priorities properly in order. And now let's do the problem next.
Okay, can I go?
Yes, sorry.
So the W will be written as like this formula, which is P0 squared times W11 plus 2PQ times W12 plus Q squared times W22, which looks like a sum of the frequency of a genotype times fitness of a genotype. So we can call this as the mean fitness of a population.
That's it. So what we've done is we started out with that R thing that's telling us how we're sampling the A1 allele differently from neutral. And then we took our big R and made these little R, R11, R12, which was exactly R11 times P squared. That was exactly the probability of sampling an A1 genotype. Then we created these W's, which weren't the R's, but were linearly proportional to the R's. And then we've gone along. So what are W1? So what are those W's? Those are something that are linearly proportional to the probability of sampling a genotype. So a value that is linearly proportional to the probability of sampling a genotype, we're going to call a fitness. So a fitness is a value proportional to the probability of sampling a genotype. And that thing, we're going to be able to think of a lot of different ways. We're going to think of some scenarios where genotypes die before they give birth to the next generation, or genotypes have a greater chance of finding a mate and therefore have a better probability of leaving offspring, or a genotype just has more offspring and therefore has a better chance of getting an allele in the next generation. So these W11s are anything that is proportional to the probability of getting a gamete in the next generation. And therefore, this proportionality constant, big W, which is created by just genotype frequency times the fitness of that genotype, summed over all genotypes, is nothing more than the mean fitness of the population. So we're now going to be able to think about how selection causes an allele frequency to change as something like, from the previous problem, a variance in allele frequency times differences in fitnesses multiplied by the frequency divided by the overall population mean fitness. So we can start talking about how allele frequencies change as really a function of the fitness of genotypes relative to the mean fitness of the population. And we've gotten here through, again, some very very elementary calculations.
Just
And-
just out of curiosity, those W terms, I imagine them being like some sort of coefficient. Are they ever like bound in certain ways, or
Yeah,
or
so,
maybe like variable too, like based on other factors?
oh yeah, absolutely. So this guy, John Gillespie, was one of the more famous population geneticists of the mid 20th century, because John Gillespie loved to think about fitnesses as random variables themselves. And and when you start allowing, when you allow this process to become sort of doubly stochastic, where you start having variances, where you start sampling alleles more or less binomially, but you start sampling fitnesses in these sort of random models, you will not be surprised that the math gets complicated, but you will also not be surprised that the solutions are just what we're doing here, but allowing ourselves to randomize over the distribution of fitnesses. And John got very famous doing very hard problems here and showing generally they had very simple solutions that had to do with whether or not the variance in fitness was large relative to the mean difference in fitnesses. That was often the answers that turned out to matter. But if you really like random fitnesses, there is no way to avoid the literature of John Gillespie. That you will immediately run into his body of work. So up next is Brooke with problem 11.
Oh, I knew my number is up. This is one that I just looked at and I was like, I have a mistake on it. Okay.
That's okay. Tell us about the mistake and tell us what the answer is.
Yeah, I'll tell you. All right, share screen. Okie dokie. So 11 was, what is the variance for this population? So knowing that this is the mean of the population, I use the definition of the variance. And the mistake that I made is that in my haste, instead of replacing these p-values, what I really wanted to do is put the probabilities for each of the alleles in question. So this should be p squared, this should be 2pq, this should be q squared. But yeah, I just plugged it in.
That is exactly correct, Brooke. You have it right, and you have understood your typo. P squared, 2pq, q squared times that. And there is a lot of algebra people can do to try to simplify that. And I'm not sure any of it is all that more informative than the formula Brooke wrote here, or possibly writing it the other way around of p squared w11 squared plus 2pq w12 squared plus q squared w22 squared minus w squared. That's sort of other formula for the variance. But you're never I don't think you're going to find a form of this that is that much cleaner or more informative than just here. Did anyone fight through this algebra to try to find something neat and were proud of themselves for getting a very clean-ish formula that they want to show? Generally doesn't happen. So good, that's great. And again, so all your life in evolution classes, you've heard stuff, people talk about mean fitness and sometimes about variance in fitness, sometimes in the context of things that are sometimes called the fundamental theorem or natural selection, various versions of that. It's a very odd word. Anyway, well, you now know what variance in fitness is. It's a pretty stupid thing. It's not, there's no deepish, there's nothing it's just that. It's just that definition. That is the variance in fitness. And you all know how to calculate it for any old values of W11, W12, and W22. And you will discover many of your colleagues over the rest of their lives are a little confused about what does people mean exactly by mean fitness? What do they mean exactly by what do they mean? They mean, those words are just that. Nothing deep, nothing confusing, nothing all of you didn't get right the first time you tried it, up to typos as a first-year student. It's easy. That's what it is. But you will hear those words if you stay in this field the rest of your life. Nothing hard, nothing deep about it. You all know how to calculate it. Mitchell, problem next. I think this was one of the Algebra E problems, was it?
Was it 12?
Yeah, yeah. Or, yeah, 12. Oh, no, even easier than the Algebra E problem.
So I just graphed
Yep, that's it.
the change in the A1 allele. I think the problem gave us the starting allelic frequency of A1 at like 0.99 and 0.01. So I graphed this. So when it was at 0.99, because I used relative fitness for these fitness measures. So the fitness for the A2 allele was the most fit. It just simply went down to fixation in both cases.
Yeah, exactly. So no matter where you start, if you start very, very high, you start very, very low, you start at an intermediate frequency, if one homozygote is fitter than the heterozygote, and the heterozygote is fitter than the other homozygote, no matter where you start, the allele associated with the most fit homozygote is going to go to frequency 1. And I'm going to, so that we get the scale exact, although your picture is exactly right, so that everyone can see the scale. I'm going to share my screen. So can you all see my problem 12? So in my problem 12, I've put 100 generations on here, sort of marked it off. You can see the scale so these fitnesses differ by, 20%, 40%, 60%. These are large fitness differences. But over 100 generations, these large fitness differences lead to one allele going to virtually zero really fast in dozens of generations. Not hundreds, not thousands, not millions, dozens. If selection results in fitness differences that are 10%, 20%, 60%, numbers that seem not huge, but are, like significant, like measurable, easily measurable, you expect, if it has this format where one of the genotypes is less fit than the heterozygote, which is less fit than the homozygote, no matter where the allele frequency currently is, in just a handful of generations, the less fit allele will be nearly gone. Does this make sense to everybody? And so when selection, and we'll talk about what a selection coefficient is, but when selection is on the scale of ones, 20%, 40%, 60%, this is almost in the number 1. When selection is on the scale of the number 1, by God, one of the alleles is gone instantly. You should, as a biologist, never ever see this in nature. If selection coefficients are this big, the allele frequency, unless you were the luckiest guy on earth, the allele frequency would have gone to 1 before you started sampling. Maybe if when the hurricane hit the island, and you know what the hurricane did to all the vegetation on the island, and you run to the island like the day after the hurricane hit, you can start watching allele frequencies change very rapidly in nature, because something about the hurricane changed really the food that was available, and suddenly little finches did much better than big finches, and you get to be very famous as Peter Grant or something. So it can happen, but you got to be there like at the right moment, because if you're a few generations late or early, there'll be nothing to see here anymore. Okay. Up next is Michelle with the next problem.
All right. Share the right screen. Okay, so basically in number 13, the A1 genotype now has the highest fitness. So it goes to, this should just say frequency of A1, not A1.
Yep.
But it goes to fixation in both cases.
Exactly. Absolutely simple, easy. And again, it is the exact same story. The A1 homozygote was more fit than the heterozygote, and the heterozygote was more fit than the other homozygote. No matter what the initial frequency is, the final frequency is going to be 1 really, really soon, or at least really close to 1. Are there any questions about that? And have I done this right? Has everybody gone? All right, Michelle, take us home then, if everybody's already gone.
Okay, well, 14, the heterozygote now has the highest fitness. So the frequency of A1 hits like an equilibrium point. And I think it's the same point for both instances.
Yeah.
I didn't bother to check, but.
Yep. So, well, we'll explain it next time. But yeah, oh yeah, I forgot about the problem 15. We'll let somebody else do problem 15. But for this problem, here the heterozygote is most fit. One of the homozygotes is less fit than the heterozygote. The other homozygote is less fit than the heterozygote. And this thing seems to have the property that both alleles are maintained in the population for an arbitrarily long period of time. And in fact, the way you've drawn it here, it looks like both alleles are being maintained at frequency like 1/3 or something for arbitrarily long periods of time. This will become more than intuitive when you do the next set of homework. This will become very explicit when you do the next set of homework. But the intuition should be right there, that when the heterozygote is most fit, if the A1 allele is near 100% frequency, and A1, A2 individuals are more fit than A1 individuals, the allele frequency of A1 will be declining because heterozygotes will be having more offspring than homozygote A1s, and will be declining at some rate. On the other hand, if the frequency of A1 were near 0, and almost everybody is an A2 homozygote, the A2 homozygote is less fit than the heterozygote. So the A2 allele is probably having, the A2 homozygotes are having less offspring than heterozygotes. So the A2 allele is declining in frequency. And in the end, there's a balance between the two, and you end up with a sort of intermediate frequency forever. So when a heterozygote is more fit than either homozygote categories, we end up with a intermediate frequency of both alleles. That will be the intuition, and we'll maybe prove it if we feel like it. We'll certainly derive what that intermediate frequency is and use it repeatedly in the next homework set. But does anyone currently have any questions about this intuition?
I had one about the where it caps off.
Yeah.
Is that more a function of the difference between A1's, the homozygous fitnesses? Because it looks like homozygous recessive is, or the homozygous for the A2 allele has a higher fitness, so it's like more skewed toward the A1 or A2, I mean.
So you will rapidly find out that the what is going to matter is only the fitness of the heterozygote relative to the fitnesses of the other two. The difference between the fitnesses of the other two shall not matter much.
Okay.
At all. That intuition of yours is an excellent one. It turns out it's not going to be right. And what's going to matter is really where the heterozygote is relative to the two homozygotes. And that is absolutely something you will not guess until you start doing the math. And if you do the math, you will find it is utterly trivial. That what is going to matter is H, the relation, not S per se.
Just out of curiosity, Michelle, I was just wondering how you coded this. I see there's like a small.
So the way I wrote the actual formulas in R, I think is pretty illegible, and I apologize for that. But basically for each P, I used the P before it according to this formula we found earlier. And then because W, I'm not even sure this is right, but because W depends on P.
No, you are 100% right. You should be doing this. Absolutely.
So you also have to recalculate W for each generation because it depends on P.
Right. Okay. Cool.
You are 100% correct. You also probably, if you actually plugged in values, you should see W doesn't change that much. So if you failed to do that, you would have gotten a picture that looked very much like what you'd had. It's just the exact place things would be might differ. But that is 100% correct. Oh yeah, that was how you were supposed to do it. You guys have derived these recurrence relationships of the change in frequency next generation. You have the frequency current generation. Now just plug and chug it. There is no good exact formula for the expected frequency next generation, or the expected frequency in arbitrary generation, number of generations in the future as a function of current generation under selection. There is actual formulas, but you don't want to know them. It's there. You don't want to know. They get very ugly very fast. Cool. Okay, let's cycle around to the top again, and then let's do Sheng-Chi for problem 15, part 1. I forgot I started.
I feel like if I'm doing 15, I'm gonna give away everything in one.
All right, give away everything. Get us home then. Get us done with class.
All right. Fine. So I'm supposed to compute.
Yep.
1 minus, so compute H and S respectively for questions 12 to 14. So I know that the relative fitness for A1 genotype is 1, and then in all 3 questions, and then the relative fitness for the other 2 are has been, I guess, normalized in this case. And if I just solve for S, I know that 1 minus S is the relative fitness for the A2 genotype. So S would be negative 0.33 for the question 12, 0.27 for the question 13, and negative 0.17 for question 14. So I actually do have a question on how to interpret S, because this S, I'm assuming it's like a selection coefficient.
That's what we're going to call it.
But if it's negative, then it's going to be against the, I guess, the genotype that we're setting relative to 1.
So as a general rule, what we'll decide to do to make the sign of S not matter to us is normalize everything so to the most fit homozygote. I have not had you do that here, but you've just immediately expressed, it gets confusing when you start changing the sign of S. So for most of what we'll do, we will simply normalize things so that the most fit homozygote has fitness 1, and then we can think of S as the selection coefficient, as the difference in fitness between the most fit homozygote and the other homozygote. Here, because we've normalized it to A1, the selection coefficient is negative, meaning the A1 allele, the A2 allele is not selected against, but is selected for with a selection coefficient of 0.33. And it's as you were in this field, almost everyone, when they say the word selection coefficient, mean it in the sense of it being a positive number, in the sense that the other homozygote has fitness 1 minus a positive number, and it's the way you think about how much worse the less fit homozygote is than the more fit. So it is a annoying, confusing thing if you have to constantly be talking about the sign of S and the sign of H, and we'll just, for almost everything we do and almost everything you guys see the rest of your life, people will have reoriented things so that they're going to call A1 the more fit homozygote. They're going to call its fitness 1. They're going to call P the frequency of the allele associated with the more fit homozygote, and they're going to make sure S has positive sign. That will lead us to formulae and mnemonics we can keep in our head, but will, if ever confronted with actual fitnesses, we might have to flip around which one we're going to call A1 and which one we're going to call A2, so that we have set things in a way that the A1 is the most fit. Does that make sense to everybody? So you will see formulae in the rest of the chapter that normalize things so that A1 was the most fit homozygote, and then talks about S as always a positive number, or at least S greater than or equal to 0, and HS, well, then we can start talking about H in a meaningful way. And again, any old second grader could have solved for this with or without Excel. 1 minus S equals 1.33. S is negative 0.3, negative a third. 1 minus HS equals 1.17. H must be 4.5. You all can do this with your very elementary math. Nothing fancy or crazy or deep is going on here. We are just going to get in the habit of, instead of writing our fitnesses as W11, W12, and W22, we're going to get in the habit of writing them 1 minus HS, and 1 minus S. We're going to get in the habit of talking about selection, the speed and scale of selection as functions of S. We're going to be in the habit of knowing what happens long-term by seeing what the value of H is. It's going to turn out, once you know H, you know everything there is to know. It is actually H, not S, that matters for almost anything. And you will be starting to, you will build an intuition that it is H, the dominance coefficient, whatever the hell that means, that is going to tell us the fate of an allele.
So I think,
Yeah,
just to reiterate a point you said, because I think what I did with this problem was I made the mistake of just kind of keeping the 1 minus HS and 1 minus S relative to the, not relative, but exact to the formula in Gillespie.
Good.
I wasn't ending, so I ended up not switching out like 1 minus HS is W1 over 1, 2 over W11. So I got slightly different values.
Good.
But my guess is that what needs to be done really is 1 minus HS is going to be dependent on who's the most fit of the alleles. So then you need to switch your ratios to be relative to the most fit allele. Is that correct?
Yeah, if I had you do I wrote the problem this way. This is the last time I want you to do it this way. I want for the rest of your life, you to think about just reorienting things so that the most fit homozygote has fitness 1. The least fit homozygote has fitness 1 minus S. The most fit homozygote has frequency P squared. The heterozygote has frequency 2PQ. The less fit homozygote has fitness 2Q squared. If you get in that habit, almost every formula you see in Gillespie will be immediately plug-inable. Very, very, very occasionally there'll be formulas, particularly when we start talking about variable selection, that don't quite follow that format. But the rest of history and the rest of the formula you see in population genetics will almost always be better interpreted if you just assumed A1 was the most fit homozygote and had frequency P as an allele. If someone doesn't say something different than that, they've assumed it. If it isn't really explicit that they're thinking about it some other way, just assume it's that way. I had you do this in this fashion just so, I don't know why I did it that way. Anyway, but don't do it this way anymore. Flip it around, make it, and if you want to memorize any of the formula from Gillespie, they will work beautifully if you normalize it that way. Questions? All right. We derived, as Kevin suggested, some of the most important formula in population genetics. We did it thinking we were wasting our time because it seems so damn easy. But we are now going to learn that we have really figured out how natural selection works because we have derived these sort of silly little formula the way we've done that. And homework 6 and a little bit of 7 is all going to be about how does selection work? What is the fate of alleles under various models of natural selection? And has anyone started homework 6 and have any questions about it? No one has any questions about homework 6. No one's really started it probably. It's been a rough week, but homework 6 is got more stuff for you to do and will take longer than homework 5. And you will have to have read the book in places to find formulae to apply if you don't want to rederive them yourself. But it should be not, it shouldn't be among the harder homeworks you do. It should be among the easier. It may be a bit long in places because you have to graph this or graph that or plug in this or solve for that. There may be a little more algebra. There'll be more algebra than there was this time probably. But there should be very little deep conceptual difficulties until maybe we get to the end of the simple model of fluctuating selection. That might be a little bit trickier. But otherwise, Linnea has a post. Could you please post the sections to read? Righto. Hold on, let me grab my book. So, sorry guys. So for homework 6, you will be, oh, right, you're gonna do Greenberg and Crow too. I love that. So for homework 5, which we just did, it covered Gillespie sections, basically 3.1 and 3.2. Homework 6 covers Gillespie sections 3.3 through, let's see, 3.3 through basically 3.7. And yeah, basically 3.3 through 3.7. I don't know, obviously if you have a bootleg copy, what pages those are. In my version, version 2, those are pages 64 to 90. Yeah, very good. 3.3 to 3.7, yeah, 65 to 90 in my version of the book. If you have a version of the book that has not only changed the pages but changed the section numbers, the sections you're looking for are really sort of basically just the beginning of the selection all the way through selection in a changing environment, in a random environment. And if your copy of the book doesn't talk about selection in a random environment, you almost surely have a first edition or some amalgamation of first and second edition. I'm pretty sure the changing environment stuff was only in the second edition, but I can't remember for sure. Other questions? All right. Well, give it a go. If you're banging your head against a problem for too long, drop me an email. And if it's not in the middle of the night, I might just respond. And we'll see you guys Tuesday with homework 6.
Sorry, one thing I just noticed with number 11 is the page numbers.
Yep.
That just really, I guess that's probably going to be related to section 3.
Yeah, I would so look at the last bit of it.
Okay.
Let's talk about genetic load. What does genetic load mean? What does genetic load not mean? There will surely, no matter what version of the book you have, there will be certainly sections, pages that talk about genetic load and what it means, what it doesn't mean, maybe. And you should read there will be problems about genetic load and you should read about it. And we're going to discuss genetic load. That's what that says. Wherever they are in your book.
Awesome, thanks.
Other questions? All right. See you guys Tuesday.